Hey everybody, these are the notes for homework number 14. This is part one, graphing exponential and logarithmic functions. There'll be a part two, which will be pretty short, which is the difference quotient. So let's get started. So graphing exponential and logarithmic functions. We're really just going to start off with some examples and talk about kind of the important things we need to make sure that we graph. So we're going to graph f of x equal to 2 to the x. What makes it exponential is that you have a base raised to the power that's a variable. It's like 3 to the x, 4 to the x, e to the x would all be exponential functions. And we're going to make a table of values. So we're going to plug in some x values. Let's actually start with x equal to 3. So I plug in 3 for x, I'm going to get 2 to the third, which is equal to 8. If I plug in 2, I'm going to get 2 squared, which is 4. If I plug in 1, I'm going to get 2 to the first, which is 2. Plug in 0, I'm going to get 2 to the 0, which is 1. If I plug in -1, 2 to the -1 is 1 over 2 to the first. If I plug in -2, 2 to the -2 is 1 over 2 squared, which is 1/4. If I plug in -3, I get 2 to the -3rd, which is 1 over 2 cubed, which is 1 over 8. We can see here that as the x values get larger, the y values get larger. As the x values get more negative, the y values get smaller and smaller, closer and closer to 0. Let's plot these points. So x is 0, y is 1, x is 1, y is 2, x is 2, y is 4, x is 3, y is 8. And then these other ones to the left are a little bit harder to graph very nicely. So if x is -1, I get 1/2. If x is -2, I get 1/4. If x is -3, I get 1/8. Okay, that looks decent enough. And then we have this sort of shape, and this is pretty standard exponential function shape. We have this long tail to the left, and then it gets really, really steep as you go to the right. A couple things to observe here. The domain of this function is all real numbers. The range of this function is all positive numbers. You can't quite get to 0, but you can get any number larger than 0. So the range is all positive numbers from 0 exclusive to infinity. Finally, some of the features of this graph. We have a y-intercept at the point 0, 1. We don't have an x-intercept, right? Again, because this graph can never equal 0, right? 0 isn't in the range. You'll never be able to touch the x-axis. And then lastly, this graph has a horizontal asymptote at y equal to 0. And we can kind of just see that. And I should say it's really just to the left here. That doesn't really matter. So unlike the rational function we've talked about before, where you compare degrees, you don't really do that for exponential functions. Exponential functions almost always have a horizontal asymptote, usually on the side where the exponent gets really, really negative. There is not a vertical asymptote here. I want to make that super clear. Exponential functions have horizontal asymptotes. They do not have vertical asymptotes. We'll see that the opposite is true for logarithmic functions because they're inverse functions. Let's graph another one. Let's see. Yes, cool. So let's graph y equals 3 to the x. So what I want to point out is for these graphs, I don't really want to plot 7 points. I could. What I really want to do is I want to plot like 1 point, maybe 2 points, and then just know that the shape looks like that. So I'm going to plot the point 0, 1, because it's always good to plot the intercepts. And I'm going to plot the point. So I know that if x equals 0, y is going to equal 3 to the 0, which is 1. And if x equals 1, y is going to equal 3 to the 1, which is 3. So there's those 2 points. I know it's not a straight line, though. It's still going to have this same shape. It's going to have that classic exponential shape. It's going to be a little bit steeper because my base is a little bit larger. If you want, you can plot one more point. Like if x is -1, y is going to equal 3 to the -1, which is 1/3. Then we're just going to kind of draw the usual shape. We have a horizontal asymptote again, which is hard to make it look like it's decreasing, right? I kind of just drew it like it's flat. And then it's just going to be exponential shape, like whoops, try to make it look good. Again, I really should stress here, there isn't a vertical asymptote there. Right? It just keeps moving to the right and getting larger and larger and larger. There isn't a vertical line that kind of prevents us from doing things with that. Let's get that back in focus there. There we go. And that's kind of all you need. I'll point out again, you have a horizontal asymptote of y equal to 0. You have a y-intercept of 0, 1. and you have the same domain and range. I don't want to write it again, but I will. I don't want to, but I will. So most of your standard exponential functions, if you haven't transformed them by shifting them or reflecting them, have these four attributes. Horizontal asymptote, that's the x-axis or y equals 0, a y-intercept of 1, domain everything, range all positive numbers. And usually, well, actually, I'll say that for a second. So let's continue on. See if I have room. Let me make some room over here on my table. This is just a little too small for this operation. Oh well. So let's look at this next one here. We're going to graph f of x equal to 1/2 to the x. And we are going to plot points here just because I want to see one particularly important thing. So let's start again with the 3 because that's easiest for me. So 1/2 to the third is 1/2 times 1/2 times 1/2, which is 1/8. You could also think of it as 1 to the third over 2 to the third. 1 to any power is 1, and 2 to the third is 8. And if we do 1/2 squared, it's going to be 1/4. And 1/2 to the first is just 1/2. And 1/2 to the 0th is 1. Anything to the 0th power is 1, except for 0. 0 to the 0th is weird. 1/2 to the -1 is the reciprocal of 1/2, which is 2. 1/2 to the -2nd is the same as 2 squared, which is 4. Right? It's the reciprocal of 1/2, and then you change the sign of the power. Finally, 1/2 to the -3rd is 2 to the third, which is 8. So it looks like we've actually done a reflection in the y-axis because our x values changed from positive to negative and negative to positive, and the y value stayed the same. So it's kind of like graphing 2 to the -x. In fact, it's exactly like graphing 2 to the -x. Let's plot these points. So we've got 0, 1. We've got 1, 1/2, 2, 1/4, 3, 1/8. To the left, -1, 2, -2, 4, -3, 8. So it looks exactly like I've taken my 2 to the x graph here. Sorry, again, I feel like this thing's not focusing very well. I've taken this 2 to the x graph and I flipped it across the y-axis. Let's see, can we see through the paper if I flip it? You can kind of see through the paper there, right? It looks like I flipped it that way. So that's what's happening over here, right? We flipped the graph across the y-axis and gotten moved. And I'm never good at drawing this one. It always turns out looking not very nice. Again, same information. I'm really not a fan of, sorry, apologies. So we have a y-intercept of 0, 1. We have a horizontal asymptote of y equal to 0. We have the same domain of everything, the same range of all positive numbers. And one thing I'll point out about this function versus the previous one is this graph is decreasing, whereas the other two graphs were increasing, right? These two graphs, the previous ones, we're getting bigger y values from left to right, right? As we move to the right, the y values get larger. That's an increasing graph or an increasing function. Here, the opposite thing is true. As we move from left to right, the y values get smaller. That's a decreasing function. I will point out that this is the same as f of x equal to, in fact, let me just show you. 1/2 is the same as 2 to the -1 to the x. And then if you have a power to a power, you multiply the powers, and that's going to be the same as 2 to the -x. So it's like we took our 2 to the x function and then did f of -x and got a reflection in the y-axis. Cool. So I know we're kind of getting to the transformations earlier than I meant to, but this is an example of a transformation. Finally, probably the most important exponential function is graphing f of x equal to e to the x. And again, there's really not a lot I want you to do here. I want you to plot the point 0, 1. I want you to draw it as usual with your horizontal asymptote to the left, and then your typical exponential shape. Ooh, that's not the best I've ever done, but you got right. It should be smooth, right? It shouldn't be any like sharp turns. There's my f of x equal to e to the x. I might label that point there. I might write down that my horizontal, I should write down that my horizontal asymptote is y equal to 0. And that's kind of it. And then if they asked about the domain of the range, once again, for exponential functions, the domain is everything. And at least if I haven't shifted it up or down, the range is going to be all positive numbers. Great. So, and this one's the most important because e is just the most important number we deal with exponential functions. It's the natural base. It's approximately 2.7, but you should just write it like this. So if I wanted to plot one more point, like if I plugged in x equal to 1, I would label this point as 1, e, not 1, 2.7. even though E is approximately 2.7. We don't approximate unless we are asked to. Okay, continuing on. So let's talk about generalizations for a second. So every exponential function, f of x equal to b to the x, has a graph like what we just drew. So a couple things I'll point out. The graph looks like this, has a y-intercept of 0, 1, as long as your base is larger than 1. So 2 to the x, 3 to the x, e to the x, 7 to the x, all those exponential functions will have a graph that essentially has this shape. And as the base gets larger, the graph gets steeper. In fact, I would encourage all of you to pull up Desmos real quick and graph something like y equals 2 to the x, y equals 3 to the x, y equals 5 to the x, just to kind of see how they look steeper as the base gets larger. On the other hand, if you have a base that's between 0 and 1, like our 1/2 to the x that we just graphed, it's going to give you that reflection across the y-axis, and it's going to look like this, which I'm, again, not usually as good at drawing. I don't know why. It just doesn't ever turn out as nice when I draw it this way. Still the same y-intercept. So for either way, you're always going to get graphs that look like that, and then you're always going to have the features of a y-intercept of 0, 1, a horizontal asymptote of y equal to 0, also known as the x-axis, a domain of everything, and a range from 0 to infinity. These things will always be true for any exponential function as long as we haven't transformed it. If you start shifting things up or down or left or right, that's going to change the y-intercept or the horizontal asymptote with the range. It won't actually affect the domain at all. The domain, you can't really mess with the domain for this function. It doesn't have any of the usual problems, right? There's no square roots, there's no fractions, there's no logarithms. So no domain issues here. That said, let's look at the next type of function. Logarithmic functions. So a reminder, I know it's been a minute since we've really talked about logarithms, but when you're finding a logarithm of something, you're finding the power that you raise the base to get the number inside of it. So for example, my favorite example, if I have a function here of log base 2 of x and I plug in 8, log base 2 of 8 is just 2 to what power equals 8, and that power is 3. Similarly, log base 2 of 4 is equal to 2 because 2 squared equals 4. Log base 2 of 2 is equal to 1 because 2 to the first equals 2. Log base 2 of 1 is equal to 0 because 2 to the 0th power is equal to 1. Log base 2 of 1/2 is equal to -1 because 2 to the -1 is equal to 1/2. Log base 2 of 1/4 is equal to -2 because 2 to the -2nd power is equal to 1/4. And finally, log base 2 of 1/8 is equal to -3 because 2 to the -3rd is equal to 1/8. Something super important I want you all to see right now. This graph has all the same x and y coordinates of my first graph, but they've been switched. If you look back at the first graph for a second, I have all those same x and y coordinates, except here it's x is 1/8 and y is -3. Here it's x is -3 and y is 1/8. And that's true for all of them, right? 1/4 -2, -2 1/4. 1/2 -1, -1 1/2. 1 0 0 1 2 1 1 2 4 2 2 4 2 8. Sorry, 8. I got it. 8 3 3 8. And we've seen just recently that if you interchange x and y, that's really getting the inverse function, or how we get the inverse function. So I want to just impress upon you the fact that, oh yeah, logarithmic functions and exponential functions are inverses of each other. So when we graph this function, it's exactly going to be the inverse of the original 2 to the x function that we graphed. So I'm just going to plot these points. Something at the point 1, 0, 2, 1, 4, 2, 8, 3. And then again, when the numbers get small, it's a little more challenging. 1/2, -1, 1/4, -2, 1/8, -3. So there's my graph. I will point out, I will draw the other graph in here just so you can really kind of see it. So just to kind of remind you, oh yeah, Here's the exponential graph. I'm gonna draw it dashed to kind of not take away as much here. So here would be my y equals 2 to the x. And here is the inverse function, f of x equal to log base 2 of x. And exactly, they're inverses because we've interchanged x and y. And notably, you can see where'd my ruler go? I had my little ruler over here. There it is. Notably, you can see that these graphs are reflections of each other across the line y equals x. If I draw the line y equals x here, you can see, oh yeah, it exactly looks like we took this original graph to the x and just flipped it across the line y equals x to get log base 2 of x. And that is always the case for logarithms. So logarithmic functions, exponential functions are inverses of each other. That said, that kind of means that all of the x and y things interchange. So going back to that, sorry, that's very loud, apologies. Going back to this original 2 to the x function here, we have a y-intercept of 0, 1, a horizontal asymptote of y equals 0, domain, everything, range, all positive numbers. Here for this logarithmic function, every xy thing changes. So instead of getting the point 0, 1, we get the point 1, 0, which is an x-intercept. Instead of getting a horizontal asymptote of y equals 0, we get an asymptote of x equals 0, aka a vertical asymptote. And instead of getting a domain of everything, we get a range of everything. Instead of getting a range of everything, from 0 to infinity, we get a domain from 0 to infinity. So the domain is 0 to infinity, all positive numbers. The range is all real numbers. Looking at this graph, we can kind of see that. Oh yeah, this graph, the x values get really, really close to 0, but we can't take a log of 0 and we can't take a log of a negative number. So your domain here is just all positive numbers. And then your range, this graph goes all the way down to negative infinity. And even though it goes really slowly here, it does keep on increasing forever and ever and ever. So it does go up to positive infinity. And then very similarly to the exponential graphs, the rest of the logarithmic graphs, if we're not transforming them in some way, are just going to all kind of have this typical shape. Meaning if I want to graph, say, f of x equal to log base 3 of x, I'm going to draw the same thing. I'm going to draw my x-intercept at 1, 0. I might choose to draw one more point, maybe like x equal to 3 and y equal to 1, right? If x equals 1, f of 1 is log base 3 of 1, which is 0, because 3 to the 0 equals 1. And if x equals 3, f of 3 is log base 3 of 3, which is 1. So I get the points exactly 1, 0, and 3, 1. I don't really think you even need the second point, to be perfectly honest, but you definitely do need the x-intercept. So I've got that point here, and then I'm just going to graph the usual shape. I've got a vertical asymptote on my y-axis, or my x equals 0, and then has this the usual logarithmic shape. I might, again, I should write down all the things. X-intercept, 1, 0. There is no y-intercept, just like for the exponential functions, there was no x-intercept. Again, excluding transformations. We're about to get to transforming these things. That's why I keep kind of saying, as long as you're not transforming them, you have all these things. A vertical asymptote is x equals 0, right? This vertical line here. Yes, the y-axis is the line x equals 0. And then the domain is once again all positive numbers. The range is once again all real numbers. And kind of like with the exponential functions, if we end up shifting this up or down or left or right, it's not going to change the range at all because you're always going to go all the way down, all the way up, but it might change the domain if we shift left or right. And it might change our vertical asymptote if we shift left or right. And it might change our x-intercept if we shift left or right. So for logarithmic functions, the range doesn't change, but everything else can change if you transform it. For exponential functions, the domain doesn't change, but everything else can change if you transform it. A couple more examples. So just like I was saying before, in general, logarithmic functions always have this shape, the usual vertical asymptote going through the point 1, 0, looking like that. And then just like before, when we graphed e to the x, now we're going to graph the natural log of x. And I'm really almost going to practically draw the same exact graph I just drew. I'm going to have an intercept at 1, 0, and I have a vertical asymptote looking like this. And then it's just going to do this usual thing. Getting larger and larger, but very slowly as you move from left to right. If you really wanted one more point, there's 2, there's 3. You could say I'm plugging in e and getting out 1. So my other point here would be the point E comma 1. But I don't even want that point really. Usual stuff. Domain, all positive numbers. Range, all real numbers. Vertical asymptote, x equals 0. X-intercept, 1 comma 0. I will also point out, just like I did kind of for 2 to the x and log base 2 of x, that y equals e to the x is the inverse or inverse function, if you like, of y equals natural log of x. And if I graph it, oh yeah, we can see that. So if I graph y equals e to the x, I'm going to get the graph that looks like this. You have to make that noise when you graph things. And look, those are exactly reflections of each other across the line, y equals x. Again, if you want to have a nicer look at these graphs, I really, really recommend pulling up Desmos and graphing y equals natural log of x and y equals e to the x, just so you can see that they really do look like this. So every exponential function and logarithmic function with the same base are inverse functions of each other. So for example, right, I said this is true for exponential and logarithmic functions. If f of x equals 2 to the x and g of x equals log base 2 of x are inverse functions. Similarly, f of x equals 3 to the x and g of x equals log base 3 of x are also inverse functions. So as long as the base is the same, those functions are inverses and they interchange the x and the y. So that's the basics of graphing exponentials and logs. One more thing I'll say about them before we start transforming them is if you look at your right hand, again, mine is not great for this because I'm old, but if you look at your right hand, you can kind of see that this line up here kind of looks like an exponential function like e to the x, and this line here kind of looks like a logarithmic function like the natural log of x. So anyway, my hands look really beat up right now. That's what rowing will do for you. So yeah, e to the x, sorry, e to the x, mine looks a little too straight for e to the x, and natural log of x. Right hand, not your left hand. Cool. Let's go ahead and look at some transformations of these. And again, we're really just going to see it by doing it. So transformations of exponential and logarithmic graphs, be sure to include the asymptotes and the intercepts. So again, a reminder, for exponential functions, we have a base to a variable power. You're always going to have a horizontal asymptote. And for logarithmic functions, where you have the log of some variable, you're always going to have a vertical asymptote. Okay, so here, this is going to be like my regular 4 to the x graph, and I'm going to shift it 1 to the right. So I don't really need to graph both of those. What I really need to do is think about what happens to my points. So normally, and I'm going to graph 4 to the x here first. So I'm going to graph, 1, 2. I don't want you to do it this way. I'm just doing it this way one time. So if I would graph just regular y equals 4 to the x for a second, I know that my y-intercept would be 1. Right? If I plug in 0 for x, I get 1 for y. And if I plug in 1 for x, I'm going to get 4 for y. So I'm going to draw this kind of dashed here. So this looks like, here we go. Sorry, again, it gets steep fast, so I try not to. Right, again, not a vertical asymptote, just get very, very steep. Okay, so now this new graph should be shifting everything 1 to the right. So before, if x was 0, my y value is 4 to the 0th 1. For this one, x has to be 1 larger. So if x equals 1, f of 1 is going to be equal to 4 to the 1 minus 1, which is 4 to the 0, which is 1. So I get that point shifted 1 to the right. Similarly, just to compare this point here, so if x was 2, f of 2 would be 4 to the 2 minus 1, which is just 4 to the 1, which is 4. So I plug in 2 for x, I get 4 for y. So both these points, the 2 points I've looked at for 4 to the x, are getting shifted 1 to the right. So this new graph is going to look like my old graph, just everything moved 1 to the right. So then graphing, it gets a little dicey because this part here kind of gets squished together. It's gonna look kind of like this. Oh, before I graphed it, I should have figured out what my y-intercept was going to be. I didn't have any up or down shift, so I know I'm still going to have a horizontal asymptote of y equals 0. I'm not going to get an x-intercept, but my y-intercept is going to be different. So to find the y-intercept, we do what we always do to find the y-intercept. We set x equal to 0. And then f of 0 is going to equal 4 to the 0 minus 1, which is 4 to the negative 1, which is 1/4. So my y-intercept is going to be the point 0, 1/4. Okay, so maybe like, it doesn't have to be perfect, but like maybe up right there. I'm going to come this way. I'm going to grab that point, that point, that point. And again, it doesn't have to be perfect. This is why I don't usually graph both of them, because I don't like to see how imperfect my graph looks. But all these points over here are 1 to the right of all these points over here. So there's my f of x equal to 4 to the x minus 1. My y-intercept, I will label the fact that my horizontal asymptote is y equal to 0. And my domain and my range didn't change at all. My domain is still all real numbers from negative infinity to infinity. My range is still all positive numbers from 0 to infinity, because I didn't move this thing up or down. Oh, sorry, you can't quite see that. Apologies. There we go. Cool. Any questions? No, I'm just kidding. It feels very natural to ask, do you have any questions, even when I'm talking to just myself? All right, let's do a few more. So now we're going to graph g of x equal to negative 3 to the x plus 9. Oh, by the way, the code word, whatever the access code for accessing this homework assignment before it is available, is the word armistice, which is not another name for Veterans Day, but is really actually what the original, right, November 11th was the day that the armistice was signed, which is the Treaty of Versailles to end World War I. Anyway, look it up. It's worth knowing about, but that is the word. It's capital A, lowercase r, M-I-S-T-I-C-E. All right, so to graph this one, we're going to have two things going on here. First, we have this negative right here, which is going to give us a vertical flip. So I'm going to just draw the little kind of graphs. So the first thing that's going to happen is my original graph would be 3 to the x, which looks vaguely like this. And then I'm going to flip it over. So my negative 3 to the x is going to look like that. Again, better than that. And then this is going to shift it up 9. So it's going to have, so my horizontal asymptote, which was y equals 0, is going to move up 9. Be something like that. And I'm going to do a better graph down here. So a couple things I noticed before I start actually just graphing away. I'm going to have a y-intercept. I'm also going to have an x-intercept here. And my new horizontal asymptote is going to be positive 9. And basically, whatever if you have an exponential function that you're shifting up or down, however much you shift it up or down, that's what your new horizontal asymptote. I said vertical, I think a minute ago. Sorry, my new horizontal asymptote is going to be that value of whatever that shift is. But let's find the intercepts, plural. So my y-intercept, well, again, if I set x equal to 0, g of 0 is going to equal negative 3 to the 0 plus 9. Now we have to be extra careful here. The exponent gets applied first. So it's not negative 3 parentheses to the 0, which would be positive 1. It's negative 3 to the 0, which is negative 1. So this 3 to the 0 happens first, and that's going to be negative 1 plus 9, which is positive 8. I'm not going to draw a whole bunch of hash marks here. My x-intercept is a little bit more interesting to find, I think. So we're going to take this equation, negative 3 to the x plus 9, and set it equal to 0, because to find the x-intercept, you're always setting the function equal to 0. The easiest way to do this, I think, is just to add 3 to the x to both sides. So I have 9 equal to positive 3 to the x, and then I know that 3 squared equals 9. If you prefer, though, you could also rewrite this as 3 squared equals 3 to the x, and then, oh, if the bases are the same, the exponents have to be the same. So x is going to equal 2. So my x-intercept is 2, 0. My y-intercept is 0, 8. My new horizontal asymptote is, in fact, y equal to 9. I would draw the horizontal asymptote first. I'm drawing that too high. That's fine. Here's my y-intercept. One below that is 0, 8. So, and I would label this. This is y equals 9. I'm going to wait to label this until I've drawn the graph. And then I'm not going to plot my point over here first. That's a bad idea. I'm just going to draw it so that I'm doing this. So it's going like this. And then come this way. Like that. So this is the point 0, comma 9, 8. And this is the point 3, comma 0. And then we might as well talk about the domain and the range. So as I said before, for exponential functions, the domain is always going to be everything. You can never have any domain issues because you don't have a fraction or a square root or a logarithm. I know the inverse function is a logarithm, but this function, g of x equal to negative 3 to the x plus 9, does not have any logarithms in it. The range, on the other hand, has changed. So now my highest y value is almost 9. And my lowest y value is all the way down to negative infinity. So I'm going to get everything from negative infinity up to almost 9. That's kind of it. Just to kind of point out like how I know that y equals, yeah, I don't know. I think really just shifting is the best way. But if you want to kind of convince yourself that you couldn't get any number equal to 9 or bigger than 9, if you pick a very, very negative number for x, like for example, if you pick x equal to negative 1,000, I just want to point out that g of negative 1,000 is equal to negative 3 to the negative 1,000 power plus 9, which I'm going to rewrite as negative 1 over 3 to the positive 1,000 power plus 9. And then I'll show you on the calculator that that number is super duper close to 9. So I probably won't even track here. 1 divided by 3 to the 1,000th power. Oh, see, it's too, 3 to the 1,000th is too big. So let's try 100th. 1 divided by 3 to the 100th. There we go. Super duper small, right? 1.94 times 10 to the negative 48th power. That means it's like 48, it's point 0 48 times, and then finally 1.94, whatever. So super small to a very, very small negative number plus 9. So this is just a tiny bit less than 9, but it's practically 9. It's like 8.9999999 for a long time, and then finally it's not 9s eventually. It's like a point whatever is left over. So very close to 9, but not very equal to 9. Let's graph a few more transformations. Okay, so here we've got y equal to 8 to the x plus 2 minus 4. So there's going to be two transformations here. You're going to take your typical 8 to the x, which again, here's your usual 8 to the x. The x plus 2 is going to shift it 2 to the left, which isn't going to really change the shape all that much. So right, this point here, 0, comma 1 is going to move 2 to the left to be negative 2, comma 1. I kind of think about where my intercept moves to, and then it's going to shift down by 4. So negative 2, comma 1 is going to shift down 4 to negative 2, negative 3. And then my horizontal asymptote was y equals 0. It's now going to be y equals negative 4. So to do something like this. Again, you don't really have to draw these little things. I just like showing you how I'm thinking about this. So I notice here that since I've shifted downwards, I'm going to have an x-intercept. Also, eventually, right, because this, even though I haven't drawn it this way, it kind of looks like I've drawn like a vertical asymptote. Let me fix my graph. This continues on to the right. It does cross the y-axis at some point and continue on, right? It doesn't have a vertical asymptote, it has a horizontal asymptote. To actually graph it, I'm going to find my x-intercept, my y-intercept, my horizontal asymptote, which I know is y equal to negative 4. I'm going to graph that right away. If the numbers aren't too big, I like drawing these little marks, but like 9 just feels too big. So here's my horizontal asymptote of y equals negative 4. And then I'm going to find my y-intercept and my x-intercept. So my y-intercept is going to be really big. So y-intercept, I mean big for a graph. If I set x equal to 0, I'm going to get y equal to 8 to the 0 plus 2 minus 4. That's going to be 8 squared, which is 64, minus 4, which is 60. Okay, so you can see why I kind of looked like it wasn't ready to get there. And then my x-intercept So this is where I probably made a poor choice marking this way. We'll live with it. My x-intercept, I'm going to set the whole thing 8 to the x plus 2 minus 4 equal to 0. I'm going to add 4 to both sides. So I'm going to have 8 to the x plus 2 equals 4. I'm going to write both sides as powers of a common base. So 8 is 2 to the third to the x plus 2. 4 is 2 squared. Then I have 2 to the 3 times x plus 2 equals 2 to the second. The powers have to equal each other. So since the bases are the same, so 3 times x plus 2 is 3x plus 6 equal to 2. Subtract 6, 3x equals negative 4. X equals negative 4 thirds. So my x-intercept should be a little bit more negative than negative 1, like right about there. And then I also would have had, I don't really need this, but I kind of talked about how I shifted my original x-intercept 2 to the left and then 4 down to get the point negative 2, negative 3. So I could also plot that point if I really wanted to. So it's going to look kind of like this. It's going to hit the point at negative 2, negative 3, which again, you don't really have to have. I just kind of wanted it. And then I'm going to have this point here, negative 4 thirds, comma 0. And then it's going to go up, 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 up. That. I'm pretend like this is the point 0, comma 60, even though my graph is not very to scale. So if you graph something like this on Desmos, you have to kind of zoom out to see that it does in fact cross from the left to the right side of the y-axis, but it does. So let's just write down all the things. My horizontal asymptote is y equals 4. My x-intercept, I know I don't know what template, write it down again, is negative 4 thirds, comma 0. My y-intercept is 0, comma 60. And domain, as usual, all real numbers. Range, we're going as low as almost negative 4 to as high as you want. Cool. All right, a few more examples. Some logarithmic shifts now. That is not the straightest graph I've ever drawn. So let's graph y equals log base 4 of x minus 1. Be careful, if I didn't write the parentheses there, so this might get written like this. If it's written like that, you're to assume that only the first thing written after the log base 4 is in the logarithm. If I wanted it to be log base 4 of parentheses x minus 1, I'd have to write parentheses around the entire x minus 1. So this is going to be a shift of 1 down, not a shift of 1 to the right. So normally, I would have the point 1, comma 0, right? If my usual x-intercept for a logarithmic graph is 1, comma 0, but that point's going to get shifted 1 down to the point 1, comma negative 1. We think about that, right? If x is 1, I know this is like not the usual point you would get, but I'm just thinking about where the one point I know is going to shift to. So I'm going to take my usual logarithmic graph, and that point there is getting shifted, that x-intercept is going to get shifted down by 1. So, and then I would find my new x-intercept as well. So to find the new x-intercept, we're going to set this whole graph equal to 0. We still can't, so I'll point out, since it's a vertical shift, we still don't have a y-intercept, right? Because we have a horizontal asymptote of x equal to 0. So to find my new x-intercept, I'm going to set log base 4 of x minus 1 equal to 0. And I'm just going to rewrite this as an exponential equation. I'm going to say, great, log base 4 of x equals 1, and then 4 to the 1 equals x. So x equals 4. So my new x-intercept is going to be 4, comma 0. So I want to be super careful here. This does not mean I'm shifting 3 to the right. It means I'm shifting everything 1 down. So and let me try and draw what would have been my original graph first. So my original graph would have gone through the point 1, comma 0. If I'm thinking of my original graph, like my non-transformed graph, as just log base 4 of x, you go through the point 1, comma 0 and 4, comma 1. My original graph would have looked like this. There's my log base 4 of graph, log base 4 of x. Then all these points are getting shifted down by 1. So my new graph is going to look like that. All those points shifted down 1 exactly. So now, horizontal asymptote of x equals 0 still. X-intercept of 4 is 0. No y-intercept. Sorry, I said horizontal asymptote, but clearly we have a vertical asymptote. Sorry about that. That's terrible. Vertical asymptote of x equal to 0. X-intercept of 4 is 0. We also have a domain that is all positive numbers and a range that is all real numbers. Okay, let's do a couple more, and then we'll be done with these graphing of exponential logarithmic functions. We're going to graph f of x equal to the natural log of x plus 2. So this is going to be your usual logarithmic graph shifted 2 to the left. I like to think about, and I probably could have said this earlier, what's happening with the domain. So over here, since I had the log base 4 of x, I knew that x had to be greater than 0, right? For logarithms, the stuff you're taking the log of has to be greater than 0. So here, I'm going to say, well, I know that x plus 2 has to be greater than 0, so x has to be greater than negative 2. So I know my domain kind of right off the bat is going to be everything from negative 2 to infinity. Negative 2 to infinity. Oh, it looks terrible. Let me try that again. My domain is going to be everything from negative. Wow, I keep trying to say negative. I keep starting to write negative infinity. Let's try that one more time over here. My domain is going to be everything from negative 2 to infinity. One thing I like about doing this in the get-go is it also kind of tells me where my new vertical asymptote is going to be. So instead of my vertical asymptote being at x equals 0, it's going to have moved 2 to the left to be at x equal to negative 2. Generally, you can find the vertical asymptote for a logarithmic function by setting the argument equal to 0. So my vertical asymptote I'm just going to get by saying, oh yeah, if I set the insides of the logarithm equal to 0, I'm going to get x equal to negative 2. To write that down there, my vertical asymptote is x equal to negative 2. Cool. So now we're also going to have, in addition to our x-intercept, we're also going to have a y-intercept because it's going to look like this. Usually your x-intercept also just kind of shifts in the same way. So since I shifted to the left, my new x-intercept should, instead of being 1 comma 0, 1 minus 2 is negative 1. So it should be negative 1 comma 0. But if you don't like doing that, you can also just set the whole thing equal to 0 to find it. So if I set the natural log of x plus 2 equal to 0 and rewrite that as, well, again, that's log base e of x plus 2 equal to 0. If I rewrite this as an exponential equation, e to the 0 equals x plus 2, or 1 equals x plus 2, or 1 minus 2 equals x, I get negative 1 equal to x. So my x-intercept is indeed negative 1 comma 0. My y-intercept, well, if I set x equal to 0, I get y equal to, let's see, if I set x equal to 0, it's going to be the natural log of 0 plus 2. So I get a y-intercept of 0 comma natural log of 2. Sorry, you can't see that. Apologies. And that's just, so I don't really need to know that the natural log of 2 is approximately, I think, 0.7. I'm just going to wing it. I'm going to say, great, my y-intercept is about right there. I don't really care. And then just try to graph, actually, what I should have done first is really just tried to graph it. And then wherever that ended up being fine with it. The usual logarithmic shape. Domain is everything from negative 2 to infinity. X-intercept, negative 1, 0. Y-intercept, 0 comma natural log of 2. I don't want a decimal approximation. And then my domain I think I already said, my range, again, for every logarithmic function, the range is always going to be everything. Cool, I think we've got one more to do. Yeah, so let's graph g of x equal to the negative log base 2 of x plus 4. So it's going to do two things. It's going to have a shift to the left again. It's also going to have a vertical flip because of the negative out here. So what I really would rather do, though, instead of trying to like do all the transformations, is just kind of think about what my intercepts are going to be. So if I want to find my y-intercept, and I know I'm going to have a y-intercept because I've shifted to the left. Actually, no, yeah. Before I do that, I should probably find my domain. That'd be so the smarter thing to do would be first to find the domain. Again, I'm just setting x plus 4 to be greater than 0, so x is going to be greater than negative 4. This also tells me that my vertical asymptote is going to be x equal to negative 4. So my domain is everything from, let's just write it down here. My domain is going to be everything from negative 4 exclusive to infinity. I know that my vertical asymptote, if I set the argument of the logarithm equal to 0, I'm going to get x equal to negative 4. It's my vertical asymptote. I should point out for logarithmic functions, we don't talk about the asymptote being opposite or the same because there's only one side of it typically. So 1, 2, 3, 4. Okay, good job. So there's my vertical asymptote. And then I'm going to find my y-intercept finally by setting x equal to 0. If I set x equal to 0, my g of 0 is going to be negative log base 2 of 0 plus 4. That's going to be negative log base 2 of 4. Ignoring the negative for a second, log base 2 of 4 is asking 2 to what power is equal to 4? Oh, 2 to the second power is equal to 4. So that's going to be negative 2. If you don't like doing it that way, you could say negative log base 2 of 4 is equal to the y value I'm trying to find, and then rewrite this as log base 2 of 4 equals negative y. 2 to the negative y equals 4. Oh, I know that 2 squared equals 4, so negative y has to equal 2, so y equals negative 2. It's a lot more of a roundabout way of getting there, but it might make more sense for some of you this way. Either way we slice it, we're going to get y equal to negative 2. So our y-intercept is 0, comma, negative 2. And then similarly, our x-intercept, well, again, our x-intercept probably just got shifted 3 to the left. Sorry, 4 to the left. I was thinking it was going to be negative 3. But we can also find it the usual way. If we set, let's see here, I want to make sure I'm not getting in the way of my graph. I'm kind of getting in the way of my graph, apologies. My x-intercept here, if I set negative log base 2 of x plus 4 equal to 0, first multiply both sides by negative 1. So log base 2 of x plus 4 equals negative 1 times 0 is 0. And then rewrite it as 2 to the 0 equals x plus 4. 1 equals x plus 4. 1 minus 4 equals x. Oh yeah, negative 3 comma 0. So our graph is going to look like this. We know it has this shape because it's your usual logarithmic graph, but it got flipped over vertically because of the negative sign right there. Domain is negative 4 to infinity. Range is everything as it always is for a logarithmic function. And then my x-intercept was negative. I'm sorry, my vertical asymptote was negative 4. My x-intercept was negative 3. My y-intercept was negative 2. Cool. I think that's about it. And then in the next video, we'll talk about the difference quotient. All right, so that is all for that.